Yes, sir.
Okay. Now, today's lecture would be very elementary because I want to repeat the part which we were discussing yesterday because I realized that uh, a few of you have got confusion while dealing with center of mass coordinate and relative coordinate. And since tomorrow is a holiday, therefore you can spend time to work out the things. I will write important steps uh, how to reduce the two body problem into one body problem, and then why we stick to relative coordinate and throw the center of mass part into the dustbin, because that will give us a foundation not only for this topic but also for the topic where we shall discuss scattering problem. Because in the case of a scattering problem also, two bodies, when we consider a particle which is interacting with another particle, like an electron nucleus scattering, proton scattering, or electron proton scattering, and then we talk about scattering cross section, then in that case also we reduce two body system and one to one body system, and we say that actually an electron is interacting with a common potential created by electron proton system. Therefore it's important to understand why one should talk about only the relative coordinate. And I am I will try my best to convince you that really it's easy to translate from center of mass from the general dependence on x, y, z, x1, y1, z1 to the relative and center of mass coordinate. Okay, therefore this will be continuation of uh, yesterday's discussion. Now you see, yesterday I wrote H naught is equal to, for hydrogen system, P1 is square by twice M1 plus P2 is square by twice M2 plus VR plus VR. This is my E naught, the unperturbed energy. Okay, this is my Hamiltonian for hydrogen atom, where an electron is revolving around the proton. But this will, what I am telling you, this will also be true for example, if I consider proton neutron inside a potential. That means if I consider a deuterium system where a deuteron is made up of a proton and a neutron, and then proton and neutron, they are moving in a common potential. Or what I have told you, that if we consider two bodies scattering, then we have a particle 1 and a particle 2, and particle 1 is interacting with particle 2, then we say that actually they are moving in a common potential and one is feeling the presence of other. Because in physics, when we talk about scattering, if electron is moving like this and it bends its path, then also we say that scattering has taken place. Or for example, a positron is coming like this, and because of the same charge, it is getting repelled. Then also we say that scattering has taken place. Because in physics, scattering is not the head-on collision. And that is why one defines impact parameter, the minimum distance of approach where one can feel the presence of the other. Okay, therefore if I write this as 1 by m1 d squared psi by dx1 squared plus d squared psi by dy1 square plus d squared psi by dz1 square plus 1 over m2 d squared psi by dx2 square plus d square psi by dy2 square plus d square psi by dz2 square plus, for a time independent problem, this will be simply E minus V psi equal to 0. Okay? The potential is independent of time, therefore the solution is not time dependent, and always we consider time independent Schrodinger equation, and we write this expression in terms of the kinetic energy part, the potential energy part, and the rest of the terms. Okay, then we introduce center of mass coordinate m1 x1 plus m2 x2 upon m1 plus m2. Similarly, y m1 y1 plus m2 y2 by m1 plus m2, z m1 z1 plus m2 z2 by m1 plus m2, and then their relative coordinate, that I should write x x2 minus x1, y y2 minus y1, and z z2 minus z. Therefore, instead of x1 y1 z1 for the particle 1 and x2 y2 z2 for the particle 2, we are defining in terms of center of mass coordinate and relative coordinate. Is it all right? And then instead of del square psi by delta x1 square, I will try to rewrite this in terms of capital X and small x and so on. Okay. Therefore, now that means we have to, instead of delta psi by delta x1, we have to write in terms of x, y, z. Therefore, if I have delta psi by delta x1, now this will be delta psi by delta x by delta x1 plus delta psi by delta y by delta x1 plus delta psi by delta z by delta x1 plus delta psi by delta x by delta x1 plus delta psi by delta y by delta x1 plus delta psi by delta z by delta x. This is how you will write delta psi by delta x1 in terms of capital X, capital Y, capital Z, small x, small y, and small z. Now, since I have already written how a capital X is related to x1 and x2 and similarly y and z, when you will put this value here, what you are going to get is this m1 upon m1 plus m2 delta psi by delta x minus delta psi by delta. Okay, because only you have x is equal to x2 minus x1, and x delta x by delta x1 is minus 1, or similarly if I have delta minus 1 here, that means I will be left with delta psi by delta x, the other quantity, since y and z, they are not depending upon x1, therefore they will not contribute. And similarly, my x was m1 x1 plus m2 x2 upon m1 plus m2. Therefore, delta x by delta x1 will simply give me m1 plus upon m1 plus m2. That is why we have only this expression. And then once you have this, then what you will do? You will try to obtain delta x squared psi by delta x1 square. And that will be delta by delta x1, delta psi by delta x1. Okay? and then you will simplify it. And when you will simplify it, again you have to write delta by delta x1 in terms of this and see where are the terms which are going to contribute. And what you will realize that this will give us m1 by m1 plus m2 whole square del square psi by delta x square minus twice m1 by m1 plus m2 del square psi by delta x plus del square psi by delta x. This will be the expression for delta square psi by delta x1 square. Therefore, first you have obtained what will be delta psi by delta x1, and then you have obtained what will be delta square psi by delta x1 square. Okay, and similarly, uh, I can, for example, obtain delta s square psi by delta y1 square and delta square psi by delta z1 square. What will be the change? Here it will be delta square psi by delta y square. Here it will be delta square by psi by delta y, and here it will be delta square psi by delta y square. And similarly for z. Therefore, what you realize that really these are very simple and trivial steps which one has to work out to obtain the quantities in the center of mass frame. Okay. Now, once we have delta squared psi by delta x1 squared, y, y1 square, z1 square, and then x2 square, y2 square, and z2 square. Now, with this, we will go back and put this in our master equation of 1 by m1 del square psi by, which I wrote, since that is not there in my slide now. Therefore, just you can see this step which I wrote 2 by h cross square e minus v psi. This is equal to 0. Now, when you will put this back, all these expression, what you are going to get is 1 by m1 plus m2 del square psi by delta x square plus del square psi by delta y square plus del square psi by delta z square plus 1 upon m1 plus 1 by m2 del square psi by delta x square plus del square psi by delta y square plus del square psi by delta z square plus 2 by h cross square e minus vr psi is equal to 0. And then you introduce the mass of the reduced system and rewrite it. Okay, when you introduce the mass of the reduced system, this complete expression you can verify. This will look like minus h square by twice m1 plus m2 d square psi by dx square plus d square psi by dy square plus d square psi by dz square minus h square by twice mu reduced mass of the system d square psi by delta x square plus del square psi by delta y square plus del square psi by delta z square plus v psi is equal to e psi, where what is mu? Mu is m1 m2 by m1 plus m2. This is what we call as the reduced mass of the system. Okay, this is what we call as the reduced mass of the system. Okay, therefore this is the simple expression that you obtain while solving second order differential equation for, instead of writing in terms of x1 y1 z1 and x2 y2 z2, in terms of capital X and small x. Now what I am telling you, that the potential does not depend upon the center of mass coordinate, that means on x y z, and therefore you can use the method of separation of variables, and you define your psi as psi r, a function that depends only on the center of mass coordinate, and is a function that only depends upon the relative coordinate, and the total energy as er plus. And you go back and put this in the expression that I wrote earlier, and write a capital M as M1 plus M2, then what you get is minus h square by twice m psi r del square by delta x square plus del square by delta y square plus del square by delta z square psi of capital R minus h square. Now psi of capital R you will take out twice mu del square by delta x square plus del square by delta y square plus del square by delta z square psi r plus potential, which depends on the only the relative coordinate, psi r and psi r is equal to er plus er psi r psi. Now what we do, we divide by, throughout the expression, we divide by psi r and simplify it. Collect the part which is purely depending upon r, capital R, and the part which purely depends upon a small r, or a part which depends upon x, y, and z, center of mass coordinate, and a part which depends upon small x, the relative coordinate, small y, and small z. Now, doing so, what you will obtain is minus h square by twice m d square del square by delta x square plus del square by delta y square plus del square by delta z square psi r is equal to er psi r, and the other expression that you will get minus h square by twice mu del square by delta x square plus del square by delta y square plus del square by delta z square psi r plus vr psi r is equal to er psi r. This is what you will get for the with an expression, second order differential equation, in terms of the center of mass coordinate, and then a second order differential equation in terms of relative coordinate. But important point is, here there is no potential dependence, and here there is VR, and therefore this is something like a free particle moving in space, because there is no potential. And for a free particle, we are aware of the solution that this should be proportional to something like e to the power p dot r. This will be where, what is this er? This is simply h square p square upon twice m. The p is related to the ER. Therefore, this will be the wave function, the particle moving in a free particle moving in a space. there, and that is why if you notice, since we, for all our physical quantities, you have psi star psi r, and therefore this guy with e to the power minus ip dot r does not play any role. Okay, therefore we don't count it in our problem, and what we are concerned with is that this part, which generally written as del square psi by del x square plus del square r plus del psi by del y square mu by h cross square e minus br psi r is equal to 0. And this, in general, you write it as minus h square by twice mu del square psi r plus Vr psi r is equal to Er psi r. This is the important expression, that you are considering electron-proton interaction, Coulombic interaction, and then you are writing this in terms of a reduced mass of the system, and you have not considered the center of mass part, because the solution is a free particle solution, and for all the physical evaluation, the like e power iet, the time independent part, was giving us e power iet by h cross, and then that we left because we said that in all the expectation values you will have e power minus iet by h cross. Therefore overall this is not going to play any role for time independent problem. Then you talk about this guy, which depends upon the relative coordinate. And this, instead of uh, writing in terms of r theta, in terms of small x, small y, and small z, we write it in spherical polar. Actually, I should write it like this. We write it in spherical polar coordinates, and when we introduce spherical polar coordinates, we write this r in terms of r theta and phi, because what I have told you, that most of the problem will be a spherically symmetric problem where there will be radial dependence and then the azimuthal dependence. We can separate it. Okay, now this psi, instead of r, or instead of writing in function of x, y, z, we write it as a function of r theta and phi. And when we introduce this in terms of r theta and phi, then what we get is an expression which is very familiar to you, 1 by r square d by dr, r square delta psi by delta r, because this depends upon r theta and phi, plus 1 by r square sine theta d by d theta sine theta delta psi r theta phi by delta theta, plus 1 by r square sine square theta del square psi r theta phi by delta phi square, plus twice mu by h cross square e minus br psi r theta phi. This is equal to 0. Just I have written del square as 1 by r square delta by delta r square delta by delta r plus 1 by r square sine theta delta by delta theta sine theta delta by delta theta plus 1 over r square sine square theta del square by delta. This is what has been taught to you in B.Sc mathematical class as well as in quantum mechanics. Okay, therefore, this is the expression which we obtain in spherical polar coordinates. And then what we do, again we try to divide this using method of separation of variables, because what we say that this guy is solely depending upon r, and this is also only purely r dependent term. Therefore we can again separate the angular part and the radial part, and we write psi r theta phi as RR, theta theta, and phi phi. Generally, we put them together and we call them by the name y theta phi, because initially what you will realize that first we have to separate the radial part and then we separate the angular part. Okay, therefore we have the radial part and we have the angular part, and when we separate the radial part, what we do, we again go back to this place and use the method of separation of variables, and we rewrite it in terms of the following expression. We rewrite it as y by r square delta by delta r square delta r over delta r plus r over r square sine theta delta over delta theta sine theta delta y by delta theta plus r square sine square theta del square y by delta phi square plus twice mu by h cross square e minus vr ry, this is equal to 0. And then we divide it by ry and separate the radial part and the angular part. We rewrite it as 1 by r delta over delta r square delta r by delta r plus twice m by h cross square. Only the radial dependence I am writing here. This is minus 1 by y, 1 by sine theta delta by delta theta sine theta delta y by delta theta plus 1 by sine square theta del square y by delta phi square. That is all. Therefore, we have one part which is purely dependent upon r and the other part which is purely dependent upon theta. And then if these two are equal, then we argue that this must be equal to a separation constant. Okay, and then we proceed from here by writing this in terms of a differential equation which is purely in capital R, and the differential equation which is purely in y theta phi. This is solved using a spherical basis function, and this is solved using associated Legendre differential equation. And this solution of this, what we call it as spherical harmonics. Okay, therefore this is how we divide the radial part, the angular part, and before that what I discussed with you was the solution in terms of small x, small y, and small z, and capital X, capital Y, and capital Z. Is it all right to everybody?
Yes, sir.
So whatever was the yesterday's question, I think some of those I have addressed it today. Okay. Now let me come back to the real problem and the fine structure of hydrogen, which I have to talk about. And since 7 minutes is left, please reconnect it, because when I will start that topic, it is better if there is no break. Okay, please reconnect. To discuss is the correction to the energy in the case of hydrogen atom. Okay, because experimentally the energy that has been found does not exactly matches with the basic concept that electron proton in the hydrogen atom is only interacted by a Coulombic interaction and there is no other effect. Later it was realized that there are other effects also which play a role, although they are not as significant as this Coulomb interaction energy part. But still, if you want to understand the experimental number, these concepts are important. And moreover, we are going to understand them using perturbation theory, okay, using this approximation method. And that means the approximation method means that this would not be the end of the story. There must be an equation which should be able to describe relativistic electrons in hydrogen atom. And when we consider the Coulombic interaction into account, that should also take into account the Coulomb interaction. And in the real world, in quantum theory, there is one equation that is known by the name Dirac equation, which is the relativistic equation for spin half particles. Okay, if you say that will be taught to you in second or third semester, relativistic Dirac equation. And then what happens when we consider a potential, how this equation gets modified. Similarly, there is an equation that is known by the name Klein-Gordon equation, that is for spin zero particles. Then you have for equations for spin 1 particles and so on. Therefore, the important point is that we will here deal with hydrogen atom problem by taking into account or by considering the different effects that modifies the ground state energy or the energy in general for the hydrogen atom. Okay, therefore my important point is that in general, when we talk about hydrogen atom problem, we write it as minus h square by twice m del square minus e square by 4 pi epsilon naught 1 by r. This is what has been taught to us in the class, and we have been also taught that the energy in the nth orbit, if you use Bohr's model, this turns out to be RH by n square, where the value RH is known as Rydberg constant, and this value is for hydrogen atom 13.6 electron volts. Okay, now if you recall, this RH is basically Ke E square whole square Me by twice h cross square, where what is Ke? This is 1 by 4 pi epsilon naught. Okay, and this E square is related to fine structure constant, and that is equal to 1 by 137. Okay, approximately this value is 1 upon 137. If you want to be a bit more realistic, this will turn out to be e square by 4 pi. This in general I write it 4 pi, but if you stick to all the units, this is 4 pi epsilon naught h cross c, because this is what we call in natural units. In natural units, h cross c epsilon naught, all of them are taken to be equal to 1. Okay, this is what we call it as natural units. For example, E equal to mc square we know. For electron, this is equal to 0.51 MeV. But in natural units, just I will write it as 0.511 MeV. Mass of the electron, mass of the proton, 938.26 MeV, and so on. Therefore, in natural units, we don't write h cross c epsilon naught. There are some few terms which we come across all the time, and we understand that the unit should be proper, but instead of writing all the time epsilon naught h cross c, simply we write it as e square by 4 pi equal to 1 upon 137. Now, if e square by 4 pi is 1 upon 137, then this term, if you notice, this is proportional to e to the power 4. And if this is proportional to e to the power 4, then that means this is proportional to alpha square, and then we have the mass of the electron. This alpha I am talking about, this is the proportionality sign. This RH is proportional to alpha square m. Okay, RH is proportional to alpha square m. This we say that the Bohr energies are of the order of alpha square m by n square. Bohr energies are of the order of alpha square m by n square. Okay, others are simply, or other would be simply remain the same regarding the corrections which we shall be talking about. Therefore, for the unperturbed Hamiltonian, for the Hamiltonian which I have written on the top, the Bohr energies are of the order of alpha square m by n square. Then our task is to consider the correction to this energy, and that is why I am writing it here, various corrections to the Bohr energies of hydrogen, starting with the Bohr energies which is proportional to or of the order of L is alpha square m. Then we have fine structure. This is of the order of alpha 4 to the power m. Then we have Lamb shift. This is of the order of alpha 5 to the power alpha 5 times m. And then we have hyperfine splitting. This is of the order of me over mp alpha 4. Therefore, what you are realizing that here this is 1 by 137 square. This is 1 by 137 to the power 4. That means if I consider this to be 100, This is of the order of 10 power minus 4. This is of the order of 10 power minus 8. This is of the order of 10 power minus 10. This is of the order of alpha 4 is 10 power minus 8, but Me upon MP, MP is mass of the proton is almost 2000 times heavier than mass of the electron. The 1000 here in the denominator, and alpha 4 is 10 power minus 8. That means this is roughly of the order of 10 power minus 11. Therefore, as you can see, the dominant will be this guy, which is still there, which is very close to the experimental observed number, but still these are the various corrections which is required to be done if we want to understand the hydrogen atom problem. Okay? And among them, what you are seeing, that this guy, the fine structure, is the most dominant, and this fine structure, we will see that the contribution to fine structure comes because of two reasons. One is relativistic correction, and the other is the spin orbit coupling. One is the relativistic correction and the other is spin orbit coupling. We will consider that my electron revolving around the nucleus is relativistic. Therefore, we must consider the relativistic correction part. Then we have to consider the orbital motion of the electron and its interaction with the spin of the proton, and that will be something like proportional to L dot x. Therefore, in this case, there are two corrections, relativistic correction and spin orbit correction. Those add to a fine structure, and as you can see, this means that both the corrections are almost of the same magnitude. Then we have a further correction, Lamb shift, and this is associated with quantization of electric field that we shall discuss in the class. And the last point is the hyperfine structure, and it is due to the magnetic interaction between the dipole moments of the electron and the proton. Okay, therefore these are the various terms which contribute to the Bohr total energy of the hydrogen atom, and these are known as the corrections to the Bohr energy. And the first that comes is the relativistic correction, and then we have spin orbit coupling. These two together contribute to fine structure, and they are, what I am telling you, are of the same magnitude, almost the same magnitude. Then we have Lamb shift, and then we have hyperfine splitting. And as you can yourself see, that magnitude of this is 10, almost 1000 times smaller than the fine structure, and this is almost million times, more than million times smaller than to what we get from the basic concept of an electron interacting with a proton through Coulombic interaction inside the hydrogen atom, and we solve the time independent Schrodinger equation. to obtain the correction to obtain the energy, and these are all the corrections to the energy. Now what I am telling you is, since you have been already taught hydrogen atom problem, therefore please try to go back to your notes and find out the expectation value of 1 by r, which is nothing but, for ground state is 1 by a naught, which is nothing but the Bohr radius, or for general this is equal to n square 1 by n square n naught, and the other quantity that is of relevance is expectation value of 1 by r square. This will turn out to be alpha l plus half n cube a square. I won't expect from you to get this. We will do it in the class. But your task is to find out that the expectation value for the ground state of hydrogen atom, this expectation value of R is nothing but Bohr radius. And since we talk about Bohr radius, and that is why we say that electrons are revolving around the proton. Mic off kar do please. Electrons are revolving around the proton in the circular orbit. Electrons are revolving around the proton in the circular orbit of finite radius. This is because what we say that in general it should be something like zigzag, because we in quantum mechanics we talk about probabilistic interpretation. But when you solve this equation, what you it turns out that the expectation value is nothing but the Bohr radius, okay, which Bohr had obtained. Even with all these corrections, you will get this value, which is nothing but half angstrom. Therefore, try to get this value by looking at your notes, and then we will try or discuss this relativistic correction on Thursday in our regular class. Okay, let me stop here. We shall continue from this class.